So yeah, this has been my project for the last 3 years. So the talk is titled Reverse Engineering the Commodore 128, or as I'd like to call it, how to find every single rabbit hole and jump into it head first. So who am I? Well, I'm just a general nerd. Computers, electronics, old cars, mechanics, you name it, I probably tinkered with it. I'm entirely self-taught. I basically have 9 years of grade school, and that's the end of my education. I've been working in enterprise IT now for 30 years. Network engineering, software developer, database admin, you name it. Once again, I've been all over the place. Yeah, it's just how I grew up, tinker with things. Why did I get into all of this stuff? Well, I got my first own computer, this exact machine, on my 10th birthday as a birthday gift. I still have it, miraculously enough. It's been dragged along in boxes and whatever all over the years. It's a bit beaten up, it's not exactly pretty anymore. Of course, when I turn it on after I wanted to use it a couple of years ago, it gave me a black screen, like Commodores do. So I wanted to repair it, and it kind of got a bit out of hand, shall we say. So further background and inspirations. So I've been following the Amiga project by John Hertel in Sweden. He, in turn, inspired a bloke in the UK called Rob Taylor, who made the 60 clone, among other things, and also the Amiga 500++, which is the one on screen there. So I was tinkering around a bit with this, and I realized that as I was repairing the 128, it had corrosion on the board. So I figured if I have corrosion on this board, other people will have the same type of problem, so maybe I should just make a new PCB you can use to repair these old machines. I mean, I want to preserve them for the future. So I set some goals to myself, because I've learned to set goals before you start projects, otherwise they will not end. So my ultimate goal is to just preserve the 128 platform. I love this machine, I always have. I wanted... Yeah, so the other thing I wanted to do is all the 128 boards, at least the wedge machines, have quite a bunch of factory fixes on the board as they come out. There's yeah. So there were little traces cut, resistors soldered on the underside, bodge wires, etc., etc. And I also wanted to try, if possible, to make small quality of life improvements, you know, the simple things that make life easier dealing with these machines. So as my goal was to preserve the platform, I wanted to use the appropriate software as such. It was always, the goal was always to make this whole thing open source. So I wanted to use an open source software to facilitate that, because if you have the open source files, I want everybody to be able to have the software to also utilize those files. I could have used Eagle or Altium or whatever, but then you have always that little threshold you have to get over. The easiest way to do this in some ways is a small German piece of software called Sprint Layout. The reason behind that is it allows you to import a bitmap image and use as a background. So you can just redraw the traces on top of that bitmap. With KiCad, I have to do it slightly differently. You can still do it, but it's possible. The other nice thing with KiCad is, of course, it's a full EDA suite. So I started doing a schematic capture. And as you can probably tell, this was actually the first time I made any substantial schematic, and it was a train wreck. It was functional, but not very useful per se. So over time, I have learned more and gotten better, so it looks a bit neater nowadays. So I kept it, it's a hierarchical layout, and I tried to keep it so that you can actually see the main blocks of the system and the buses, but all of the small control signals, etc., are just global global signals. So it's kind of a hybrid approach, but I like it quite a lot. To help me along with this, I have to say the Commodore schematics were incredibly accurate for this machine. Very, very straightforward. So I think the biggest issue I found on the original factory schematics was a missing ring on an inverting buffer on the output. That was literally it. Yeah. Everything else has been absolutely spot on. The bill of materials has some issues. But on the other hand, I always also preferred to work from the PCB and the way the PCB is set up and what components were on the actual PCBs, because that machine worked, right? So anything else can be a bit here or there, but the PCBs at least actually work. So I always tried to do that. I also did not attempt to preserve the layout of the original schematics in KiCad because it didn't really make sense to me. I can do hierarchy, I'm not limited to the amount of sheets that I can use, etc. So it made more sense to me to just start splitting them up a bit. And for certain things, I mean, do I really need to see the reset signal traced all over the place, or do I just use a global label for it? I know what the reset is, I'll use a global label. That's one of the things I learned from the first train wreck of a schematic. So now that I had the schematic entered, this took a couple of months just to make sure that I got it all in proper and learning the softwares, etc. It was time to do the PCB, and at that point, you start by taking a board and you desolder everything, right? And by desoldering it, I mean you desolder this component, you look at it, you measure it to make sure that it is what it says it's supposed to be. So you make your own BOM from the existing board.
Was that a working system, or did you sacrifice a working system?
I did sacrifice a working system for this, but I basically considered that it was for a good cause and I was going to reuse the chips anyways.
That must have been hairy that moment you decided.
Yeah, yes, to some degree. I mean, it is a nice working machine, but on the other hand, I'm going to rebuild it. So I figured, whatever. On this first one as well, I also sanded down the solder mask to get a clearer, nicer picture, which did help a bit with KiCad, because the problem with the current process of doing this in KiCad means I have to take that scanned image and convert it into a monochrome bitmap. So if I do that with the solder mask and the silk screen in place, I get a bit of a jumbled mess and it can be really hard to parse. I tried that approach at first, but it was really, really hard. I then just grabbed the board and took it with me to work, where they have nice A3 flatbed scanners, and just scanned it away. Which is a very nice way of doing this, because putting it in a flatbed scanner means you get a very consistent and predictable DPI. That makes life a lot easier later on. So when I then convert this into a component in KiCad, I can enter the DPI, and it will be dimensionally accurate, which is very, very nice. So once you do that, you import the scan as a component in KiCad. So the faint green lines is the bottom layer, and the faint blue lines are the top layer.
That's where you change the shape of the hole? Is that the hole on the left there?
Yep, exactly. It was easier to make it just a square with rounded corners. Yeah. So the first thing you do is just place all of the components, and here I learned a lesson a lot later. I should have picked a fixed grid for the components and shimmied them around a bit instead of slavishly following the original PCB, because I ended up having PCB traces that were a bit too close for holes, and I had a lot of micking around to make them nice and even and get clearances as they were supposed to be. And then you just sit down and draw all the traces. Bring patience. Lots and lots of patience. Lots of patience. And if you look at the amount of track segments down in the corner, I clicked all of those.
So did we.
Yeah, and I was just about to say exactly that, right? It was a lot of work for me. I did this over a period of about 3 months, evenings, weekends, etc., just to put it in there. And then when I was done, I realized that Bill and the boys did this in a week, and I was just copying. They had to figure out where to put all the things and calculate on all of the impedances and all of that type of stuff. And I'm just, yeah, okay, I understand the RIP comment on the back of the board now, absolutely. No kidding about that. So, yeah, that ended up pretty nicely. It was a lot of work.
Is that accurate? 14,430. Oh, I'm sorry, 464 nets.
464 nets,
Yeah,
yes. The track segments are just individual bits of tracks, yeah. So, no, that's accurate. It's probably the net segment is accurate. I have a lot more track segments than you did because I added a few tiny bits. Yeah. So once I had all of that done, I generated some gerbers, figured out how to actually order PCBs, found the only vendor that seems to be able to do a board of this size because it's 16 by 10 inches. So you look at an ATX motherboard and go, oh, that's nice and tiny.
No excuses.
Yeah. Well, I also have to say, it probably couldn't have been smaller because this thing is packed. It's a 2-layer board. Yeah. So I got all of that sorted out. I ordered my first set of prototypes, soldered one up. That took me 2.5 days to solder up the first prototype. That's when I learned the real value of having the component values on the board, which I then added on all the other revisions after this. Yeah, and as a comparison, building one for me today takes just about 6 hours from start to finish, and just hand soldering. So as you can probably tell from the wires, I got the footprint for the AV DIN completely wrong. I forgot other convenient things like, mounting holes. Who needs those? So, but I soldered it all up. I plugged it in, and it worked on the first try.
Wow.
That's amazing.
Except. And that error confused me quite a bit, because it was weird, and it was also flickering a bit. So, and then I realized I was using the international version, so if you look at the character ROM, it has this happy little carrier board. Because the original character ROM is a 2364 mask ROM from Commodore. It does not fully use a standardized JEDEC pinout. So when they sold these internationally, they wanted to put the European characters in the ROMs. They made a small carrier board to adapt the pinouts to make it work, except they couldn't make it straight through with just the pins. So there's a little cable that goes for address pin 11. I'd forgotten to connect that one. So it was just floating, and the ROM was just giving different data, just randomly. And that ended up with just, for some weird reason, some letters were lowercase. So I guess it just flowed over from the next...
What was on the bus the last?
Yeah, exactly. So I plugged that one in, and it's just been fine ever since. So I was still absolutely in shock that it actually worked on the first try. So that was interesting.
Do they have that same carrier board on C64s?
I haven't looked, actually.
Yeah, because at no time did somebody say, hey, someday there will be
Yeah.
an international chip or FOB ROM. We never even was on the radar.
That's funny. We'll come back to that one, actually.
Okay.
Yeah. So speaking of some of these fixes, so one of them is R102, which is on the schematic, but it wasn't actually on the board.
That's a series terminating resistor, I assume.
It is a resistor on the 1 megahertz clock, splitting it into two buses. Yeah, I guess it's for impedance control.
It's for absorbing the reflection.
Yeah, exactly. So that one was just stuck on. They cut a trace and they just soldered it on the underside. So, of course, I did a bit of jiggery pokery and I managed to put a place to locate it close to its original location. So that worked out fairly well. That was probably the first fix that I did on the board.
Were you aware of fixes like this? They inserted a series resistor on one of the clocks. Were they using you to keep production, or was I know Kalea did some babysitting of production?
Not too much, no.
Yeah, I didn't know there was any fixes, and there's a handful of them.
Those are probably just production engineering fixes.
Yeah.
Yeah.
I mean, at that point, later on, we definitely had real production engineering. I'm not sure about.
Oh, okay.
Yeah,
Yeah, I was gonna say, because I'm normally pretty good about putting those resistors in there.
Yeah. And then the next fix that I have documented here is one of the jumpers, which is, there's a jumper that will allow you to use larger ROMs, which were then used in the DCR later on. So you could have 2 ROMs instead of 4 for the system ROMs. It's drawn as A14 in the 128 schematic, as A15 in the DCR, and A15 is what it needs to be. Yeah. So I actually did a trial run before I fully understood the reasoning behind this one. I actually did a trial run where I put a jumper for A14 or A15. That board never were stable. Just adding that jumper and those 2 address lines a bit too close, it made the board meta-stable. It worked for an hour and then it would just freeze and then you reset it and it worked for a little while longer. Certain demos tended to just trigger it to freeze instantly. It would just crash exactly here. So,
You just described my nightmare scenario while working on
Yeah.
gameplay.
Yeah.
It just fails every now and then. That would be the worst thing.
Yeah. So those things are just a nightmare to debug and troubleshoot, obviously. Yeah. So,
In 1980.
yeah. So,
Right.
coming back to the international one, J7 jumper on the board is documented as using either the 128/64 mode signal or the caps lock key for selecting which font to use in the ROM. So, at some point this was thought about for being internationalization, right? It would have had to be. Yeah. Yeah. However, if you look on the J7 jumper, you will quickly find that it's not very useful.
We didn't use it.
Yeah. So what they ended up doing, as on the left-hand side for the international machines, they cut a trace and soldered in a budge wire, the brown one. So whenever you find a machine with that little carrier board for the EEPROM character ROM, you will also find this budge wire in place. So what I did was I just reran the traces and made this jumper work. So now you can just jumper between caps lock or 128/64 mode for the font ROM. So that was pretty much bringing it back to the intention of the schematic in essence. So there were a few more fixes. I didn't put them on slides, unfortunately. One of them, which I discussed with Bill earlier, is for the read-write signal coming out of the CPU complex. There was an additional gate added before it went to all the chips in the system, except for one chip, which is the VDC chip, the 80-column video chip. And I thought once again that it might have been something for impedance or whatever. But as I was discussing it with Bill, he mentioned that, yeah, no, we did that intentionally because we wanted the VDC chip to get the read-write signal a bit before everybody else. So they added an extra buffer gate, a driver gate, just to delay the read-write to the rest of the system, probably to make the VDC a bit more stable. I'm not going to say stable, just a bit more. So yeah, that was pretty interesting. I'm sure there were more little things like that that I did. I didn't keep a change log when I was working on this either, unfortunately. I should have. Lessons learned, I do now. So at that point, I was pretty much done with this PCB. I'm working on a few small fixes, just more quality of life, breaking out the address bus on headers so that it's easier to do mods for users. Some of the restore signals, the XROM and game signals, you know, the type of things you might want to tap into for doing modifications. I also brought out, there's one pin on the AV DIN that is not used, it's unconnected. I brought that one out on a pin, so if you want to install a second SID, you can just bring this audio signal out there without having to do silly things. And just because I could, I put a jumper to ground the audio in to avoid any noise leaking into the SID chip. Yeah. And just small things like that all over the board. The other thing I did on the latest revision, which I should have put up here as well, is I added guard traces, so just ground traces around the video signals coming out of the VIC chip. So I just grounded on both sides, all the way out from underneath the chip. And I was expecting it to have a bit of a help a bit with the jail bar issue, because the 128s are fairly notorious for having severe jail bars. And to my surprise, when I started one of those boards the first time, the jail bars were gone, almost gone. There's really faint traces of them left, which I suspect is not going to be fixable easily because they're probably from inside the chip. Because the 1 megahertz signal is sitting right next to the video outputs.
Yeah, I think that was our assumption at the time. Is
Yeah.
I never tried to troubleshoot that noise. I troubleshoot
Yeah.
ground noise. But I assumed it came out of the chip noisy. So I'm impressed you were able to. Now I'm kicking myself going, oh, we could have done that.
Yeah, yeah, no.
We could have put that ground in there.
And really interestingly,
We had an extra day, yeah.
leading up to the next slide, I've done some other PCB work since. So I managed to locate and find one of these, which is a 128 CR board. That's a cost-reduced version of the 128 wedge machine. Not a lot of people are even aware this exists. I wasn't until I really started digging around in things. There's no official schematics that I've found anywhere. And yeah, exactly. Yeah, the only reference I have ever found, official reference I have ever found to this board's existence is in the original Commodore kernel source code, where revision 6 has a reference that this is to support this board, etc. Yeah. So I reversed engineered that board, and as I kind of expected from the start, it is the DCR board design with the floppy drive portion chopped off and with a new power supply bit stuck onto it. Yeah.
Yeah, but I don't recall where it came from.
So it was
What did they do with the Z80 clock? I figured it was Germany because they did not like our Z80 clock.
yeah. So I reversed engineer that board once again, desolder all the things, measure everything, build a BOM, do the schematic, etc. And that's now the only existing schematic for that board that I'm aware of. So I did not fully finish reverse engineering the PCB because it's very handy to work on both the schematic and the PCB at the same time, obviously, because the schematic validates the PCB, which validates the schematic. It just goes both ways. You always compare it to the board. If the schematic is off, you can't connect the trace in KiCad. So it's very useful having both of them available. So I didn't finish that board. All the signal traces are done. I just did not finish all the copper fills and all the power connections because I was pretty tired at that point, so I will pick it up and finish that at some point. It's also a bit odd, this board, because it's slightly smaller than a 128 board. It's about an inch shorter on each side. So I don't think it's much of a difference to make any significant cost saving, especially when you consider that if they wanted to, yeah, and if they wanted to make it efficient use of it, they'd have to tool a new case. Yeah. So what they did instead is they just heat inserts into the original case. So they're easy to locate by just flipping the case, and if you see these brass inserts heat pressed into the case, it's going to be one of these. So I also brought along one of the finished articles. So unfortunately, I could not find somewhere that would do this with hard gold on the edge connectors. Oh, I can find plenty of places that will do it for me, but I'd rather buy a house, I think. So JLC PCB will do this with ENIG for a decent amount of money. And I've tested their ENIG plating on the card edge connectors, and it seems to be fairly robust, I have to say. And besides, if it breaks, you just build a new one. So, that's pretty much what I've done for those parts. I started reversing the 128 DCR just to complete the collection, because that's the last PCB revision that I'm aware of. Unless Dreen in Argentina did something really weird with theirs. But as far as I understand, the Dreen 128 was only sold in a couple of hundreds in total, so I don't have much hope of ever finding one. Yeah, and I'm also planning on doing the 128D drive board, because it is a 1571, but it does not have the same shape as the standard 1571 board. So just for completeness, I want to do that one as well. So that's pretty much what I've done for all of the PCB work. In parallel, I bought a microscope. I was using that one just for surface mount. That's what I bought it for. So, and at some point, of course, you get interested in, you start seeing people looking at silicon inside the chips, etc., and you get kind of half interested, but I really didn't want to start digging into all of those nasty chemicals. So decapping a chip, so just decapsulating it, removing it from the epoxy, the traditional way is using fuming red nitric acid at 60 degrees centigrade. Yeah. Which should be enough to make most people just go, whoa, 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 hang on, no, please. The other option, which is slightly nicer, is you can use rosin.
Use what?
Rosin. Just like you would use rosin flux. You can use the actual resin from conifer trees. Chuck it in a test tube, chuck the packaged chip in there, heat it up on a Bunsen burner, let it simmer for a long time, and it will actually slowly eat away at the epoxy. Yeah. So that's a lot more gentle. Yeah, it's largely inert, but it is a bit etching, so it slowly eats away at the epoxy, and it seems to leave the dye itself alone. So that was all right. I was planning on tinkering with it when I found a YouTube video by a Frenchman called Antoine. I've discussed quite a bit with him since, because we share our hobby with microscopes nowadays. And what he did, he came up with a clever trick of just taking the packaged dye and heating it with a hot air gun, or your hot air station, to about 350 degrees, at which point the epoxy actually becomes brittle. So now you can crack it off just using a pair of pliers, and of course most of these boards have this little ship carrier sitting underneath it like a metal plate, so if you're really nice and careful and gentle, it takes a bit of practice, you can actually pop the dye out with no problem. It comes out nice and clean as well, which is really nice. I was really surprised. I watched the video and I went, that looks easy, let's try it.
What happens to the bond wire? Yeah, exactly.
You rip them off.
And they don't tear the pads off?
Sometimes they tear the pad off, but that doesn't bring a lot of the rest of the ship.
It's not like a PC board
No, 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 it just rips a hole in the pad and
Right,
that's it. So it works pretty all right. Often they actually get stuck, they rip somewhere else. And my solution to that has been you chuck the whole die into the ultrasound and they just fall off.
I have never talked to a person that used the sentence, yeah, we just
Yep.
ripped the bond wires off.
Yeah. So if you're interested in that one, the YouTube video is actually called Chips à l'Antoine. Yeah, so that one is actually pretty nice, interesting to watch because it is pretty fun actually to crack these things open. And yeah, I did have a jar of busted MOS chips, so I didn't sacrifice anything working for it. So what I did was I took the PLA apart. So I just cracked one open. The image on the left is the first image I ever took of a silicon chip, so the actual die inside. The one on the right is my first interpretation. I pinned out where the legs went by figuring out where the power connections are. They're fairly simple to locate. And then I started quickly seeing the difference between an input pin and an output pin, because the output pins have power drivers. Yeah. So by just looking at those things, I could figure out what the individual pins were on the package, and now I'm starting to get a bit interested. Yeah. So I bought a microscope. So at this point, I'm going up to slightly bigger boys. This is a metallurgical microscope from Amscope. When you get into some proper magnification, of course, you will not cover the whole die with just a single photograph. So you need to motorize it. Motorized microscopes are expensive. So I found a new rabbit hole of building CNC hardware. So I built my own, I motorized this one all on my own. The one on the picture here has motorized XY and also tip and tilt. Because the way I work is I glue the silicon dies to a microscope slide. And of course, you never get them full level because the backside is a bit gritty and etc. So I use the, it's just a small tip and tilt table from optics labs. They use them for leveling lasers and those type of things. And it works just fine to just level it out so that I can move in X and Y without losing focus too much. It's a bit of a trick to get it balanced, but you figure it out. And to keep it nice and simple, I had an Amscope camera that I bought with the microscope. It's nice, it's adapted to the optics, but it does not run in Linux at all. And in fact, it doesn't really have any proper drivers per se. You have to use their application. I didn't like it. So I ended up using the Raspberry Pi high-quality camera that you can buy now for decent enough money. It comes with a C-mount, and the microscope actually had a C-mount. So that was pretty nice and convenient. I just slapped it on there, and it worked pretty fine. It's not parfocal with the eyepieces, so you have one focus setting for the camera and another focus setting for when you want to watch it through the eyepieces, but that's what it is. Then I built a small control board on the side, just using normal stepper motor drivers and an ESP32. So that worked out pretty nice. So I get some better pictures. So a PLA is, of course, divided. You have an AND matrix on the inputs, and you have an OR matrix for the outputs. And then you have product terms connecting the two. So on this image, you have on the AND matrix, you have 2 pins for each input. To make things easier, you have the straight input, and you have an inverted for each one. And the first image on the left is the full die with all the layers intact. The second one on the right, now we're back to nasty chemicals again, because I also quickly realized I will not be able to decode this by just looking at the top metal layer. It obscures too much of things. So this is all covered with glass. So when they manufacture these things, the last thing they put on top is a layer of glass to passivate it, so keep oxygen away from the actual silicon. I learned this, and I found it really hard to find information about how these were manufactured and what the different things do. because most of the modern stuff that you can find on the internet is CMOS, which caught on for some reason, and this stuff is all NMOS. So they don't work the same way. NMOS, in this case, is RTL. And if you do FPGAs, you instantly think register transfer logic. But in this case, it's resistor transistor. So eventually, I ended up buying a book, this book, which might be familiar to some people. This is Large-Scale Introduction to VLSI System by Conway and Mead. And this is a very nice university textbook from the late 70s. I think this is the second printing from 1980, which describes how NMOS was designed and manufactured. It has all the bits on how to lay out NMOS logic. I didn't need much of that. I just wanted to understand how the chips were made. I'm still not going to learn how all the mathematics that go into making a working NMOS chip. I just need to understand enough so that I can pick them apart. So that's how I learned all of these glass layers inside. And of course, how do you get rid of glass? There's pretty much only one chemical that will do it, and it's not a nice one. It is hydrofluoric acid, yes. Or as many chemists calls it, the piss of Satan. There is a nice video on that as well, Decapping Ship, the simple and easy way, where they talk about a lot of this, including all of the chemicals and how to do it, etc., etc. Because a lot of people also want to decap ships and have them still work afterwards. I never had that constraint, so I didn't really bother looking into all that much. So what I did was, of course, I can't just go off and buy hydrofluoric acid. I live in Europe. They won't sell it to me. So, industrial cleaners, yes. Porcelain etchers used by dentists. I tried to buy some. They wouldn't sell it to me. That's 9% hydrofluoric. Eventually, I realized that a lot of hobby people etch glass. How do they etch glass? It has to be hydrofluoric acid. So I realized that Armor Etch glass stainer is 3% hydrofluoric acid, which worked perfect for me because I don't really want a higher concentration. 3% allows me to have a slow and controlled process, so I can remove certain layers if I want to. If I remove all the glass, you end up with what I have on the right picture, everything removed. What you have left there is basically the diffused substrate of the silicon itself. All the metal, all the polysilicon, all the glass, everything is gone. But that was pretty much what I needed for this. I've later learned how to control the process so I can just take off the passivation layer, because it also works as a lens when you take pictures. It's a glass layer, so you get diffusion and light diffraction and yeah, all of that nasty that you don't really want when you take pictures. So by doing this, if you look at the right-hand picture, you can see that certain things look different. And that's when I realized that the PLA chip in the 128 was basically programmed in the diffusion layer. So they put different things in. If you put these things in the diffusion layer, you get a transistor, otherwise you do not.
Yeah, we call them diffusion slugs.
Yeah.
We programmed it with preloading contacts and diffusion slugs.
Yeah. And it becomes even more obvious when you look at the other matrix, the OR matrix, right, where it is blindingly obvious how these things were programmed. So this one was really easy to decode. So once I had the AND matrix and the OR matrix, of course, you then sit down and have fun for a while to figure all of this out by just looking at the images.
That's a visualization of a
Yeah.
good day.
Yeah. I put this into a spreadsheet just to keep track of things, but I made a few mistakes along the path. You can find all of this on my GitHub, including the captured images in Krita, which I used to do all of this work, and also the spreadsheet. So if anybody else feels up to validate it, feel free. So now I had the and the or matrix and all the product terms and everything else figured out. Of course, now comes the trick. If we go back to the original image, I have this mystery box at the bottom. I have the AND matrix, I have the OR matrix. What's all that stuff at the bottom there? It's connected to all the outputs. So if I want to understand this chip, I have to figure out what those things do, right? It's a repeated block of logic. Each block looks a bit like this.
I know what it is.
So the first image on the left is the full shot with all the layers intact. Now I have gotten a bit better at the microscoping, as you can probably tell. The middle image is with everything scraped up except the substrate and the diffusion. And the third image is me having fun in Inkscape, tracing all of the bits out. So you trace it all out in Inkscape, you use different colors. So I just had a layer for each of the layer inside the chip. So blue is metal, red is polysilicon, green is diffusion, and yellow is a contact hole. Yeah. Yeah, exactly. And the black ones are, of course, the slugs going straight through, so the vias. What you can't see in here, but you can actually tell apart if you look. So the I don't have my mouse pointer. Yeah, there we go. You can look at this one here, for example, the T1, and you see that it's really wide, the red thing. That tells something to somebody who does NMOS, especially when you have the little yellow bit at the top. So it's connected at one end of it, and if you know NMOS, you know that this is a depletion mode transistor. So, and that's usually connected to VCC on these things. It's a small pull-up resistor made out of a MOSFET. It's a very poor pull-up, but it does enough to do the job. Whereas these thin red lines are actual resistors, transistors, so MOSFETs. And I stared at this for quite some time, and then I just sat down with pen and paper and started breaking it out a bit more. And then I loaded it into KiCad and did this. So now you have a logic diagram, and you can actually look at things a bit more. And the things with the fat red line, the fat line, that's a depletion mode transistor. And you can see pretty much all of them have the gate connected to the source. I hope I got the direction right there. I'm still a bit confused about source and drain, because when you go down to the silicon, they're all the same.
Yeah, I was to say,
Yeah.
they're interchangeable.
Yeah, exactly. So that's actually working like a pull-up resistor. Its NMOS is always going to be a pull-up resistor. In PMOS, it will always be a pull-down resistor. And the other ones are pretty much just normal gates. So if you look down in the corner, where's my mouse pointer? There you go. This one is fairly telling, for example. That's an inverter. So you have a pull-up on the output, and the input goes to the gate, which pulls it down. It's an inverter. So by looking at all of this, and with some help from my trusted book, I could figure out what all of this did and break it down into something that's a bit more recognizable. Now you have the actual logic gates that went into building that thing. And looking at the logic gate configuration, it's a D-latch. So at that point, I basically figured out that, well, certain things are latched on the outputs. In the DRAM write enable has a latch, and the other one is for the, I can't remember straight out of my head, but it's one of the bus arbitration lines. AAC, yeah, AAC. Also has a latch on it, on the output. So there has been some attempts to reverse engineer the PLA before, like they did with the C64, because the C64 PLA is fully combinatorial. If you present this set of inputs, you will get this set of outputs. And they have struggled to do the same on the 128, not only because it's a much larger PLA, but also because they got confusing results. You did a run, you tried it again, and you get a slightly different result. And that's because of these latches. So it's really hard to reverse engineer a latch to design from fiddling with the inputs. So after I figured this out, and I had the matrices decoded, you can write Verilog. Great, now we just have to learn Verilog. I picked Verilog over VHDL, which is more popular in Europe. Yeah. Simply because the open source tool chains, there are some now for FPGAs, Yosis, etc., are really good at Verilog and not very good at VHDL. So I just picked Verilog because, hey, I like open source, right? So you can find all of this code at that URL, that's my GitHub. And some debugging later. I actually had a 128 running using this PLA chip. I still had some issues that have since been resolved, but yes, there are machines now running with PLAs. I think Evie from Backbit is actually selling a PLA replacement for the 128, which is based on this reverse engineering effort. So it works. I have some chips I use myself to test around with. This is a bit exaggerated. What I was doing here is I connected all the inputs and all the outputs because I wanted to compare on both chips. So at this point, I'm actually running the original PLA and my PLA in parallel. All the inputs are connected to both, and the outputs are separate, because I wanted to determine the difference in propagation delays between the two chips. I have since learned that the 128 is surprisingly tolerant to a PLA being a lot faster than the original one. So the original one has a propagation delay of about 35.
They require minimum delays
Yeah.
in C64, especially for the
Yeah.
CAS timing, especially for CAS.
Correct.
And we hated minimum delays.
Yeah. Well, you did a good job, because the original chip has a 35 nanosecond propagation delay, input to output. And I think you had a budget of 40, if I remember correctly.
Yes,
Yeah.
40, yeah.
And the XC95XL that I'm using has about 6 nanoseconds, and the system works just fine. Yeah, which is really impressive. So since then, I've started working on the MMU chip. I've taken one of those apart and had a quick look around as well. That one is a lot more complicated. I needed a better microscope, so I bought a microscope. Once again, ignore my spelling, please. I built a whole motorization stack. This one is fully motorized. I have X, Y, I have tip tilt, I have Z-axis, because I want to start playing with focus stacking, and I have a manual rotation on it. So that one is a lot more competent. I'm not fully finished building it up yet. But I've also already started getting involved in reverse engineering some other machines, the Mac SE's BBU chip, for example. I have imaged the original BBU, and we also managed to find a Brainstorm Technologies BBU, which is the overclock device for those systems. So we're working on reversing that one as well now. It's pretty interesting. Anybody interested in this type of stuff, just come to my desk and chat away. Yeah. My future plans on this topic is I'm going to try and finish doing the MMU. I don't really need to do a silicon reversing for the MMU. The documentation is really good, so it's good enough for me to re-implement the MMU. Then I'm going to go to the other chip that's unique for the 128. And there, I'm probably not going to reverse engineer the chip per se. I'm going to re-implement it in a fashion that I find a lot more usable. To start with, drive it off the system clock. And a few other things like that, mostly because there's not a lot of people using the VDC in a custom manner. They drive it through the kernel, and at that point, I mean, who cares, really? And a few other things like that, but I really want to try and make it a good representation of what I think that chip should be. Much better than the one that's in there, at least. Maybe have the IRQ line hooked up. And the ultimate goal for me is to be able to build a brand new 128 from completely new parts. But I also don't want to just shove it into a single FPGA, because for me, that's the same as just running it in an emulator, really. As I usually say, I like having a data bus I can just put my finger on. Yeah. So, yeah, that's pretty much it for me. So, if you have any questions right now, I'll take them. Otherwise, I'll be at my desk for the entire weekend and just come over and chat. I will probably try and have a actual working exhibit. I'm actually going to be sat there working on the MMU code and some of the PLA stuff. So, yeah.
Bill, how do you feel watching somebody recreate your work?
I'm way past asking why, because I fully understand what he's doing, right? No, it's amazing, and I had forgotten about those D flip-flops, though I had remembered that we had made a flip-flop through the PLA as a transparent one, but then you said, there was something odd about the PLA, and this whole thing happened in my head where I'm like, oh, we added flip-flops!
Yeah.
So.
No, it's been interesting. I've been chatting with Bill along the process for quite some time, and I think I'm dragging up a lot of horrors from his repressed memories at times.
And could one of you give me some more details, the differences between the 64 PLA and the 128 PLA?
Go ahead.
Oh yeah, no, sure. The C64 PLA was basically a pirate copy of the Signetics S100. Yep. I think that's 82S100. Yeah, correct. So the first machines actually used the original 82S100, I think. Later on, that was not cost effective, so what they did was they just re-implemented the exact same thing. They probably took it under a microscope and looked at it.
We had the Polaroid picture stuck to it.
Yeah, there you go. Yeah.
Up in the R&D lab.
And they just recreated the exact same chip on their own and just made it non-programmable. It's just programmed in a mask somewhere. Right. And as far as I understood, the high failure rate on those chips is due to a process failure. I think there was too much boron in some layer, passivation layer probably. Right. Yeah, which caused it to basically just, you get oxygen leaking into it and just destroying the chip over time. Because what a lot of people understand that heat will kill a machine, right? Warmer is not nice, but most people tend to forget that when it comes to actual chips, the temperature starts at 0 degrees Kelvin, not 0 degrees centigrade.
Room temperature is still temperature.
Room temperature is still about, what, 300 and something Kelvin, right? It's pretty warm. And when you look at it from that perspective, having another 20 or 40 degrees centigrade is not going to make that much of a difference. So a chip sitting on a shelf will still degrade. Yeah. And oxygen is really bad stuff.
I just learned from talking with Albert Charpentier that it was Bob Yanis who originally used the 82S100 on the C64.
All right.
So that's the genesis of that, which I never knew until recently.
Oh, that's cool indeed.
The one that went and pulled it and said, yeah, this is what we're going to use.
Yeah.
So, go ahead.
Was that the theft of the Signetics design before mask work was copyrightable in the United States? Is that how it worked, and there wasn't a patent applicable, or what was the deal with copying a Signetics?
It was borrowing, not theft.
I see. Well, that got repaid, I guess, when Nintendo stole the 6502 and just deleted 4 transistors in order to make the the decimal mode not work.
No, I don't remember anybody ever going, oh, we're going to get in trouble for doing this.
Yeah.
It's like, keep going.
Yeah. So, any other questions? Yeah, there you go.
Out of curiosity, what is the deal on the 128 with all the capacitors on the bottom right side? What do they do?
The bottom right side next to the keyboard connector?
Yeah.
Yeah, those are actually feed-through capacitors. So it's, in essence, ferrite beads or very low impedance inductors with a capacitor in the middle of them connected to ground. So what it works as is basically a low-grade, low-pass filter. They are there not because they are necessary to make the computer work, they are there to make FCC happy. Yeah. Yeah. So because when you, yeah.
When Japan, Tokyo, Japan showed us that,
Yeah.
we fell in love with it.
Yeah, correct. And if you look at the 128 board, it's pretty noisy. There's a lot of TTL stuff on there. They're working at megahertz speed, which is slow today, but you also have to remember they're doing 5-volt swings, right? They move a lot of current up and down. So when you connect a cable to something external, you have now connected an antenna to a large uncontrolled radio appliance. So those filters will basically try and remove a lot of that noise from entering into external connections.
I have a question. Did you ever track down that VCF line on the PLA?
It is there in the PLA, yes. I haven't
Figure out what it did? Is it still used, I guess?
I haven't looked into the exact details. It does change a few of which product terms are used for the AES.
Yeah,
It's related to the AES somewhat. Yeah,
And the D-flops made it so we didn't need
yeah,
VCF.
correct. It's something like that. I'll look into it later. I still need to validate and clean up the Verilog code to make it not, because I wrote it so I have all the product terms and then I combine the product terms. So it's downright ugly Verilog, but it works.
So I think why the D-flops were needed on the gate, I think we performed a gated rewrite function.
Yeah.
And what we found was the VIC chip was going, okay, on to the next cycle. Wait a minute, where are you going with the read-write line? I was
Yeah.
writing here.
Yeah.
Right? And you left, and I was doing a write, or
Yeah.
let it Twitter, even on
Yeah,
1
correct.
nanosecond,
The-
will kill a read-write cycle.
The one thing I have run into with using modern logic in replacing the original PLA is I get really short 1-2 nanosecond spikes on the outputs because the input signals come slightly different times. The original PLA is so slow that it never reacts, but a modern CPLD, it just goes, oh, well, it's combinatorial, we need that spike there.
Yeah, it was a big capacitor,
Yeah,
grid,
yeah.
basically, yeah.
So I haven't seen a bad effect from that yet, but I'm still working on trying to filter those out because I don't like the RF and noise from it. Yeah. Yep.
So you had an example where between chips, a delay of an extra gate was important for stabilizing, maybe deglitching a signal. But was trace length or trace capacitance important on this board, or not at the speed it was being used here?
Well, let's see what you said.
Oh, there is impedance issues, all right.
Well, we did no impedance control because it was
Yeah.
a two-layer board.
Yeah.
So to answer your question, things were so slow back then that we generally didn't have a problem with the speed of propagation. It would actually reflect and echo and settle
Yeah.
down, and we waited for it to settle down. So we didn't have to drive it where it was valid within a nanosecond or whatever 6 inches would be of travel.
Except for the bod wire.
Yeah. Which was crosstalk.
It's crosstalk, yeah.
Yeah,
And
yeah.
yeah. So no, it's a very big board, so you get a lot of noise on there, but these chips are very tolerant in general. Yeah.
So you know that wire that's on the 128 on the top? We cut that. We actually did a video show with it. And I was expecting it to be something like it was ringing, and it turned out to just be crosstalk in there. But I thought it was a propagation back and forth. I thought it rang like a bell. And it was just, it got too close to another signal at a bad point in time.
Yeah.
So it was, yeah.
Yeah, I've not had to implement that on any of the Neo boards. I've always had CPM working without it, and
I wish I had done it in a video output. Now that you've said, hey, it can be improved, I'm like,
Yeah.
why didn't we at least try and do video impedance control? And I know the answer is there was no time.
yeah, yeah, exactly. So, yep. Well, I think we're out of time, so thank you all.